Our objective is to develop biocompatible polymers that are capable of binding to calcium ions, and the design of monomers will be determined from the results of quantum chemical calculations. So we start with the Diketopiperazine structure. It's the smallest cyclic dipeptide. It's stable under physiological conditions and yet is highly bioactive. It can be formed from any of the 20 amino acids or that form proteins and also their analogues. Diketopiperazine can be synthesized from standard solid-phase peptide chemistry procedures using Bach and FMOC synthetic systems. So here we show the Diketopiperazine analogues from both alpha and beta amino acids. On the top right, you see two alpha glycol residues forming a 6-membered ring, and below it, the combination of of two beta amino acids forms an 8-membered ring. When one alpha amino acid and one beta amino acid are combined, you get a 7-membered ring. Now this was done both in the case of glycylene amino acids and proline amino acids. So the stability and the reactivity of each of the monomers will be compared. Here are some computational chemistry details. The geometry of all the monomers were optimized at the B3LIP 631G level of theory in the gas phase. And the single point calculations were carried out using couple cluster calculations with single, double, and a non-iterative perturbative treatment of the triple excitations. So to compare the stability of each of the monomers, we use isodesmic reactions. Here we combine two alpha amino amides and two beta amino amides to synthesize the 6-membered prolyl ring, and the resulting two beta amino amides are shown on the results side. And this was done to form the 6-membered ring of proline, 7-membered ring of proline, and the 8-membered ring of proline. So the same series of reactions were also done in the case of glycine. And this enabled the stability of each of the monomers, all 6 of them, to be compared on the same energy scale. So this figure shows the results. As you see, the 6-membered rings in both cases are the most stable, whereas as the ring size increased, the stability increased slightly. Well, it increased slightly in the case of the glycine amino acids, but when proline was used, as you can see, the increase was more drastic. So now each of the monomers underwent a series of polymerization reactions. First, nucleophilic addition took place at the carbonyl carbon of the amide, and then which initiated the ring opening step. And finally, the anion was protonated in the final step. So in the case of the 7-membered rings, you have two different reaction sites. So this is why you have 2 reactions to show the 2 analogous steps. And this reaction would take place for all 6 or all 8 of the monomers. Each of the 3 reactions took place for all 8 of the monomers. So this table summarizes the results. As you can see, the structure of all the monomers and the corresponding color to each of the energetics, the changing of free energy for each of the 3 reactions described earlier. So you can see the nucleophilic addition, the 7-membered rings involving the glycol residue was the most energetically favorable. In the second series, you see the 7-membered ring, whereas the first in this analog had the most energetically favorable. And also the same was true for the 8-membered ring. But from combining the 3 reactions, we could see the 7-membered ring was most favorable with Gly because you had negative value for the addition, for the ring opening, and the protonation. So from this data, we conclude that the 7-membered ring involving 2 glycol amino acids is the most stable. So then from this, we went and we already synthesized the 7-membered ring structures.